Okay, we're going to look in this video at the idea of graphing a rational function following these guidelines, and we're also going to algebraically find the range of this rational function. Okay, I'm going to make this a little bit bigger, so if you want to, you can pause the video and read it in more detail. But we're going to go through these steps one at a time. And I've added on the fact that we can use calculus to find the first derivative and locate relative maximums and minimums, and we can use the second derivative, the test for concavity, to find any points of inflection. So this could really be number 8 here, where we're finally going to sketch the graph. Okay, so let's go through this. We want to find the x-intercepts. That happens when y is equal to 0. And if we try to solve this quadratic equation, here's proof that it doesn't have any real solutions. The discriminant is -8. If you try to use the quadratic formula, you'll have the opposite of be plus or minus the square root of -8. So therefore no real solutions. So there's no x-intercepts. Now to find the real roots of the denominator, we'll do that in order to find the vertical asymptotes. So we got to use the quadratic formula, or completing the square. Here are the roots for the denominator, and here are some values, and that's what these red dashed lines are. This is the line x equals 0.149, and this is the line, the vertical line, x equals 3.35. Okay, and that will come into play later. So the point of locating these vertical asymptotes is that the graph can never cross those red dashed lines. On the other hand, well, let's find the y-intercept first. The y-intercept happens when x equals 0. It's easy to picture these terms disappearing if you substitute 0, so there's your y-intercept right there, 0, 3. So we're building up the sketch of the graph. And this is something, if you were doing this for homework, you'd probably do this on scrap paper, all these steps, and build up to your final graph. The horizontal asymptote occurs by taking the limit as x approaches either plus or minus infinity. And it turns out that y equals 1/2 is the horizontal asymptote, which I haven't sketched in here yet. But it would go something like that. And here's why that works. If I divide through by x squared, which is just another way to write the original function, divide every term by the highest degree, the coefficients of these x, the highest degree term, determine the horizontal asymptote. This occurs when the degree of the denominator equals the degree of the numerator. There's your horizontal asymptote. Now it's possible for the graph to actually cross its horizontal asymptote, but as x approaches infinity, we'll get closer and closer to the horizontal asymptote, but we'll never touch it. We got to find the one point where this graph might cross its horizontal asymptote, and that's what we're going to do in step 6. So we want to ask the question, does the function ever have a value of 1/2? And if we cross multiply, we get this. Solve for x, we get x equals -5/11. And at -5/11, we can plug that into the original function. I've shown the steps to do this manually. We've got a complex fraction here. So if we multiply every term in the numerator and denominator by the least common denominator of all the little denominators, 121, it does simplify to 1/2. So there is the point where this graph crosses the the horizontal asymptote, and that's the only point at which the horizontal asymptote can be crossed. There's no other ones. So that means if we find some points down in here that satisfy the function, that it can't ever go above that horizontal asymptote. It probably has to turn around and come down. Or if it's up in here, it's got to go this way. So that's why we want to locate the horizontal any points on the graph that are on the horizontal asymptote. It helps us sketch the graph. Now, we're getting into some calculus. Use the first derivative test to identify relative max and mins, intervals of increasing, decreasing. So here's the original function. Here's f prime using the quotient rule, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. If you multiply these polynomials together, combine similar terms, this is what you get. That's f prime. We want to find critical numbers, which occur when the first derivative is equal to 0 or undefined. And this will equal 0 when the numerator is equal to 0. In other words, if you put an equal 0 out here and multiplied both sides by this denominator, then you'd get this. Although I multiplied through by -1 to change the signs, use the quadratic formula. There are the points where the first derivative is equal to 0, -1.97 and 1.06. Recall the vertical asymptotes that are approximately 0.15 and 0.34. It's a good idea to put the critical numbers on the number line. This is actually a first derivative test. Now here's the -1.97, here's the 1.06, and I've also put the vertical asymptotes with x's here and dashed lines to represent the vertical asymptotes. So we want to test numbers in each interval created by these critical numbers. So it turns out that if I put -2 into this first derivative function right here, I get a negative number. So to the left of -1.97, f prime is negative. That means the original function is decreasing. And similarly for all these other points. Oh, and by the way, I also determined the function values at those critical numbers. That's what we have to put on the graph. So there they are. But the point is, we've got a relative minimum right here at -1.97, 0.1304. And we got a relative max because the function went from increasing to decreasing between the vertical asymptotes at 1.06. And the function value at 1.06 is -1.5 approximately. Okay, so let's see what we've got so far. Here's the y-intercept. Here is the point where the graph crosses its horizontal asymptote. Here's a relative minimum. That means this function is coming down to here, and that's the lowest it ever gets in the neighborhood of that point. And we'll talk about behavior at the vertical asymptotes in a minute. Here's the relative maximum, and to get the sketch up here, we have to the right of this vertical asymptote, we have to decide if the graph is above the horizontal asymptote or below. So pick a trial number. F of 4 is 5.4. That tells you we're up here, and we'll probably go something like that. Now, to identify whether the graph approaches positive infinity or negative infinity as it gets close to its vertical asymptotes, this is essentially what we're doing, although these are approximations here. Taking the limit of f of x as x gets close to this vertical asymptote from the left, and as it gets close to this vertical asymptote from the right, and same over here. You can do that by substituting values close to the vertical asymptote and seeing whether you get any big numbers, an absolute value, or very negative large values for positive infinity and negative infinity. And usually you can tell just by the way the graph looks. You don't have to necessarily do this. Second derivative test for concavity, points of inflection, intervals of concavity. Here's f prime. It's really messy to find f double prime. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. That derivative of the denominator, we have to use the power rule followed by the chain rule, all over the denominator squared. Now here's a key technique when you get a problem like this. Notice that on either side of this minus sign there is a polynomial 2x squared minus 7x plus 1. So you can factor that out. And I actually factored out a negative 2 from both terms on either side of that minus sign. So inside the parentheses I still have one factor of this. Factored a negative 2 out of here, that's 11x minus 5. Oops, plus 5. I just typed that wrong. And over here we've got this. This is gone, and we've got the 4x minus 7, and the 2 was factored out, and that's why this negative sign became a plus, because I factored out a negative 2. Anyway, after you simplify it, this is what you get for the second derivative. And notice that we canceled out one of these. Okay, now, when does the second derivative equal 0? That's going to be the test for concavity. Here was the second derivative. When does the numerator equal 0? Well, here. Now what I did here in this table is use Newton's method to determine the root of this polynomial, this first derivative, the second derivative, and it turns out it's about negative 3.63. Okay, and so that's the only place where the second derivative equals 0. Here's those vertical asymptotes with x's and dashed vertical lines, and a reminder, here were the vertical asymptotes, so those on the number line are approximations. And here is a table that tells us the sign of the second derivative in all the intervals created by these numbers. So to the left of negative 3.63, the second derivative is negative. Think of a frown. Negative equals frown, so the original function is concave downward. Between negative 3.63 and 0.15, like 0, the second derivative is positive, so concave upward, and similarly concave downward, concave upward. This is a point of inflection right here. Let's see, I don't think I showed what its x value or y value is. but maybe on the next board. Okay, so find the range of f of x algebraically. In other words, what are the possible y values depending on x? Well, one way to do that is to realize that the range of this function is the same as the domain of its inverse. So I like to interchange x and y and solve for y. You don't have to do it that way. But here I interchanged x, and now I'm going to solve this equation for y if possible. And then we're going to find out any restrictions on x. And those restrictions will let us determine the domain of the original, the range of the original function. Sorry. So if I multiply both sides by this denominator, x times 2y squared minus 7y plus 1 gives us this, and equals y squared plus 2y plus 3. I'm going to subtract all these terms, move that transpose to the left side, and here are the terms with y squared, here are the terms with the y, and here's what we call the constant term. So in effect, this is a quadratic equation in terms of y. So a is the 2x minus 1, b is the coefficient of y, c is the constant term. We don't actually have to use the complete quadratic formula. We want to examine the discriminant, which is b squared, right here, minus 4ac. And that simplifies to this. And in order for this equation to have real roots, the discriminant has to be greater than or equal to 0. Because you can't take the square root of a negative number in the real number system. So 41x squared plus 56 minus 8, when is that greater than or equal to 0? Well, over here, I found out when it's equal to 0 using the quadratic formula. So that's about negative 1.5 and 0.13. And then I use test numbers in each interval to determine whether values in that interval produce positive values or negative values. In other words, if I put negative 2 in for this x, I get a positive number. And that'll be true for any numbers to the left of negative 1.4962. And 0 gives me a negative number, and 2 gives me a positive, so that's your solution set. Numbers greater than less than negative 1.49 or greater than 0.1304. So that's the range of f. It's the domain of its inverse function. All right, so what have we got so far? Here's what the graph looks like. Vertical asymptotes, horizontal asymptote. Oh, we lost some stuff here. So I'll just point this out. These are just random points to find out basically how the curve goes to the right of this rightmost vertical asymptote. Over here we have the y-intercept. We have the point where the graph crosses its horizontal asymptote. We have the relative minimum right here. That's the low point. That's where the tangent line has a slope of 0. And here's the point of inflection. That's where the concavity changes. So this, you can't really tell that it's concave downward until we reach that point, and then it turns to concave upward. Here is the relative maximum, and the curve goes through that relative maximum. Picked a couple other points to help plot the curve, but here's the observation. none of these values are in the range of y. We went from negative 1.496 up to 0.03. Those numbers are not in the range. Okay, we found that algebraically on board 12. Okay, finally, let's go to here and actually see the tangent line moving. So here's the tangent line, there's the point of inflection, there's the relative minimum where the horizontal tangent line is horizontal. I come down to here, I probably can't get it set right there exactly, but that relative maximum is where the tangent line is horizontal. Concave downward, the curve is always above its tangent line. And if I move over here, curve is concave upward, tangent line is underneath the curve. Okay, so there you go. Hope that helped. If you have any questions, well, hopefully you enjoyed the video. There you go. Let's end it.